Ladies and gentlemen, this presentation shows the scope of research presented in the manuscript entitled Modeling and Simulation of Vibro-isolator Rapid Prototyping Using Additive Manufacturing, compiled by the authors, Nitter, Blazejewski and Królikowski, from Koszalin University of Technology in Poland. This work is a combination of two areas of knowledge related to research in the field of human protection against vibrations and additive manufacturing technologies. The presentation will run according to the following agenda. 1. Introduction. The aim of the research. 2. Physical model of the vibro-isolator and its geometry. 3. Mechanical concept of a vibro-isolator model. 4. Research on the frequency and form of natural vibrations of this model. 5. Particular model frequency analysis. 6. Additive manufacturing technologies and material used in model research. And finally, summary and conclusions. Many factors decide about the performance and functional properties of vibration damping elements. Among other things, these are physical, mechanical, and material factors. The mechanical properties of natural materials include the tested, limited range. An example is the Poisson's ratio. The Poisson ratio of known and so far developed natural materials is positive, with some notable exceptions. The mechanical and physical properties of most natural materials are integral. This can be considered as an example of the modulus of elasticity and density, and therefore porosity of certain classes of materials, including most cellular materials, are interrelated by the energy law. These limitations limit the design space and the practical uses of materials. It is therefore desirable to develop materials that could show any chosen set of mechanical and physical properties. Artificially produced mechanical metamaterials are the best method to use the new properties in practice. Metamaterials made of deliberately designed microstructures that supply the mechanical properties programmed with a suitable geometric or topological design. Understanding and showing the key mechanical characteristics of metamaterials is a prerequisite for their implementation. A clear classification of the emerging mechanical metamaterials based on mechanics not resolved yet. Typical mechanical metamaterials are closely correlated with four elastic constants, Young's modulus, E. Structural properties of any real material, homogeneous or not, can compared under elastic stress. Poisson's ratio can define as the relative amount of how a given material contracts laterally during axial stretching. Metamaterial mechanisms consist of a single block of material whose cells interact with each other in a precisely defined way to obtain a designed macroscopic motion. The key element here is the specialized cell type, the character of which is found by shear capacity. Metamaterials are artificial structures, usually with repeating patterns of internal junction nodes. Unusual properties owe their geometry to the material they made of. Metamaterial structures have optimized by algorithms defining the programmed direction of motion, considering the results of experimental research. The artificially created geometry belongs to the family of metamaterials. The concept of metamaterial has expanded from electromagnetics and acoustics to mechanics. Composite structures are not entirely new to the field of mechanical engineering. The methods of three-dimensional design of these engineering microstructures in the literature appeared recently, especially regarding atypical macroscopic properties. Typically, mechanical metamaterials have improved mechanical properties, such as zero or negative Poisson ratios, atrophic shear modulus, negative stiffness, negative compressibility, peculiarly nonlinear behavior and non-standard topological microstructures, all of which distinguish them from conventional natural materials. The development of mechanical metamaterials favored by advances in the incremental method, in other words 3D printing with high resolution. Typical mechanical metamaterials characterized by four constants: the Young E module, the Kirchhoff G module, the mass module K, and the Poisson ratio. The first three of them are responsible for the stiffness and compressibility of material from the engineering point of view. At this stage, the results of optimization of structural topology using the basic design principles, in combination with experimental studies, to obtain various mechanical properties that are counterintuitive. The metamaterial has a deformable structure and activating elements that can controlled and computer simulated using the finite element method. In one aspect, it resembles a composite in which the communication between the constituent materials or the shape and arrangement of the constituent materials is dynamically controlled to affect the mechanical properties of the metamaterial. The construction of structures depends on their intended use. All structures should be of the same size and geometry, set in such a way that they perform specific tasks in the simulation using the finite element method. During the initial tests, an element considered to replace a spring in which there is a linear dependence of the elastic force F on the spring deflection from the equilibrium position X. See formula in the slide, where K, coefficient of elasticity, spring constant, determines the increase in force with the deflection of the spring. Composites can also be multifunctional materials, minimize size and weight, both as controlled mechanical components and as supporting structures. One of such multifunctional applications is intelligent or circular leather, which has a protective, adaptive, and functional function, e.g., absorbs energy. The presented research constitutes the initial stage of work on the durability of components printed on spatial printers in various technologies. At this stage, the SLS, Selective Laser Sintering, method used detailed dimensions of the considered Model 1 can see in the slide. By combining the approach presented above in the field of modern manufacturing techniques with the use of metamaterials, it is possible to set a new direction for rapid design, prototyping of machine and device elements. An example in this work is an element that absorbs vibration energy, e.g., seat suspensions of drivers of heavy goods vehicles or working machines. The comfort and safety of drivers depends on the vibro-isolating properties of these suspension elements. This problem widely researched and discussed in two directions: passive and active suspensions. First, the properties of the prototype under compressive tangential load investigated. The perpendicular force of the surface A shown in figure loaded, and the element mounted on the surface B, here all degrees of freedom are fixed. The figure in this slide shows the directions and values of displacement of the vibro-isolator elements under a load of 1N. The directions of the arrows indicate a characteristic, dominant, oscillating movement during loading. The simulation tests of the model show the linear characteristic of the vibro-isolator. The dependent variable is the value of displacements U, shown in colored figure of individual points of the circle system, and the values of stress S described by equations for linear elastic bodies in the form presented by above formulas, in the range of small deformation values. Stresses in relation to deformations does the Duhamel-Hook law. C is the stiffness tensor. Tensors S0 and ε0 are the stresses and initial deformations in the material, respectively. When the stress and displacement tensors are symmetrical, the stresses can write as the product of the stiffness and strain matrices. Usually, it is not so, and the product in the second equation in the system replaced by an action marked with a symbol, which means summing up the products of tensor elements with respect to two indices. With linearized displacements, the relations between strains and displacements describe the Cauchy dependencies, represented by the third equation in the system. To determine the mechanical properties of the vibro-isolator, first the frequency and form of the internal vibrations of the model were evaluated. They allowed to indicate the frequency range, which guarantees minimization of the probability of the occurrence of undesirable resonance vibrations generating excessive vibration amplitudes, and even damage to the element. The natural frequency and mode shapes obtained using the FEM-jumped element method by solving the three equations shown in this slide. The natural vibration analysis considered the material that was selected and used to produce both the model and the prototype of the vibro-isolator. The mechanical property of the material influencing the tested parameters is the material density, Poisson number, and Young's modulus. They obtained using the data from table shown. The Poisson number assumed to be 0.5, value like rubber. In all simulations, Young's modulus calculated based on hardness, according to the relationship presented below the table. The parametric analysis, hardness parameter of the own task showed that the number of frequencies and the form of vibrations are similar and independent of the tested parameter. Hardness was 30, 40, 50, 60 short d. On the other hand, the natural frequencies change. Figure shows the first 16 frequencies and modes of natural vibrations of the model with the parameter hardness equals 60 short d. As it results from the analysis of the results shown, the shape of the model guarantees the frequency ranges in which the occurrence of resonance minimized, excluded. With the hardness equals 50 short d parameter, the eigen vibrations form do not change, while the successive values of the eigen frequencies change and are respectively in hertz. As can be seen, the natural, resonant frequencies in the examined low frequency range can be grouped into bands in which they appear close to each other and those in which they are separated from each other. Such a band of separated frequencies can be determined in the range from 40 Hz, determined by the third natural frequency for the model with a hardness of 60 short d and 84 Hz. Determined by the third natural frequency for the model with a hardness of 30 short d, the span of the band is 44 Hz. The second band has 15 and 16 natural frequencies, about 15 Hz wide. The analysis of the eigenvalues also shows that the properties of the material have, in addition to the geometry of the Vibro-isolator, an influence on the occurrence of the above-mentioned bands. To verify the correctness of the identification of the frequency bands in which the Vibro-isolator is characterized by the desired damping properties, i.e., subjected to periodic loads, it will not induce internal resonances. Simulations were conducted with harmonic excitation. The first test was conducted by simulating the load of a model built of a material with a hardness equals 60 short d and a frequency close to the third natural frequency, a harmonic load of 1n, on the same surface as in the case of static tests. Figures A and B show the result of loading with a harmonic force with an amplitude 1n and frequencies lying inside the band, where there are no natural frequencies. For the tested material with hardness equals 60 short d, the range is from 39.034 Hz to 120.89 Hz. The deformations shown in the scale 1 and the stress values are within the safe range. Stresses do not exceed the tensile stress at break values in table in previous slide. However, as shown in Fig C and D, at frequencies close to 120 Hz and awfully close 121 Hz to the natural frequency of 120.89 Hz, strain and stress build up and then exceed the allowable tensile stress at break limits. In the case shown in Figure D, the Vibro-isolator would fail. In the range between 6 and 7 natural frequencies, as shown by the results in Figures E and F, the deformations and stresses are again in the safe range. The risk of unwanted resonance disappears. Material used in the research is a TPU for 3D printing and selective laser sintering technology. The modeled structure printed on a Sintradec 3D printer made of Sintradec TPU material. The material specification explained table in this slide. The study of vibration isolators made of metamaterials gave promising results. Results signify that, while maintaining the same dimensional parameters, be able to model stiffness of the tested elements. Confirmation of the research in experimental will confirm the serviceability of the assumed concept and will contribute to the development of a new method of designing elements so that the external dimensions are the same. The dimensional identity will result in the fact that it will be possible to use unified sockets for machines and devices by modeling only internal parameters, which will allow for optimization of production processes. By adjusting the fill density, we can adjust the stiffness of the damper, which will affect the vibration reduction effectiveness. Changes in macro geometry can result in a change in stiffness when loaded perpendicular to the coordinate axis. Research work will consider changes in the macro and micro geometry of the Vibro-isolator, as well as the filling density. Thank you for your attention. This presentation was prepared by the authors, Remigiusz, Andrzej Blazejewski and Tomasz Królikowski as part of the conference. 26th International Conference on Knowledge-Based and Intelligent Information and Engineering Systems concerned the paper titled Modeling and Simulation of Vibro-isolator Rapid Prototyping Using Additive Manufacturing.